In this video we're going to explain how to understand the general properties of two-dimensional linear ordinary differential equations in terms of the so-called Tor delta plane. So what we're looking at a problem like this. X dot is Ax. So x is a two-dimensional vector evolving over time, and so we can consider the time derivative x dot or dx by dt, and that's going to be given by Ax, where A is a matrix, so a 2 by 2 matrix like this. X is a vector, A is a matrix, Ax is a vector again. Okay. So this matrix, capital A, is like A, B, C, D. And so basic properties of this are going to be controlled by two numbers, Tor and delta. So Tor is the trace of A, which is the sum of the diagonal entries, so that's A plus D. And delta is the determinant of A, which is AD minus BC. And these two numbers, they control the characteristic polynomial. Remember, the characteristic polynomial is defined to be the determinant of t times the identity minus a, and that ends up being t minus a times t minus d minus bc. You expand that out, you're going to get t squared as your quadratic term, and then you get the term in t is going to be, you get a minus at and a minus dt, so it's minus a plus dt, or in other words, minus tor t. And then the constant term, it just ends up being AD minus BC, which is delta. So our characteristic polynomial is t squared minus tor t plus delta. Quadratic polynomial, and the roots, or in other words, the eigenvalues of the original matrix A. So they're the roots. They're given by the standard quadratic formula. You get tor plus or minus the square root of tor squared minus 4 delta, all divided by 2. And remember the way the roots and the coefficients work. The Tor is going to be, this means your characteristic polynomial is going to be t minus lambda 1 times t minus lambda 2. You expand that out and compare with what you've got here. You find that Tor is going to be the sum, lambda 1 plus lambda 2, and delta is the product, lambda 1 times lambda 2. Okay, so we can, we've got this diagram here where you're along your horizontal axis is labelled by the trace, which is Tor, and the vertical thing is determined by the determinant, which is the det A, which is delta. So this is the Tor delta plane. Tor is the horizontal coordinate, delta is the vertical coordinate. And so it might happen that delta is negative. Okay, so this is the line where delta is 0, and then the region below here, that's where delta is negative. And for systems where delta is negative, we've got what's called a saddle. Okay, the delta is negative, and then Tor squared minus 4 delta, minus 4 delta is going to be positive. So this Tor squared plus minus 4 delta, that's a positive, and the square root is a real number. And so we've just got two real roots, lambda 1 and lambda 2. But the product of those two roots, remember, lambda 1 times lambda 2 is going to be delta, which is negative, which means one of them's got to be positive, the other one's got to be negative. Okay, so your lambda 1 here with the plus sign, that's going to be a positive real number, and lambda 2 is going to be a negative real number. Okay, and what happens is, you get corresponding eigenvectors, v1 and v2, and so multiples of little v1, that's going to be a line through the origin. Multiples of v2, that's another line through the origin. And you've got solution curves, they kind of converge onto these lines. So we'll just have a look at the picture like this. Okay, so this is an example of such a system. One of these lines is, you've got these two lines here. These are the multiples, of the two different eigenvectors. And we can see how the system behaves. Right? You've got points evolving over time, so we can draw some points here and we see how they evolve. And we see that they kind of flow out along the pink line. So this pink line here, that's going to be the eigenvectors for lambda 1, the positive eigenvalue, and then the blue line here is the eigenvectors for the negative eigenvalue. If we try and put a point exactly on the blue line, it's not very easy to do that exactly, but then you'll kind of flow approximately along the blue line, and if you were exactly on the blue line, then you would just flow down towards the origin and you just sit there. But we missed slightly, didn't quite get on the blue line, and so as we approach the origin, it turns out we're going to sort of veer just slightly sideways, and then as soon as we've started to veer sideways, we're going to get pulled onto the pink line, and we go out to infinity along the pink line. That's how it works. So this is not a stable equilibrium. If you start near here, then you're going to get pulled out along the pink line. Okay, so that's what's meant by a saddle. Then different possibility, we could have a stable node. Now stable nodes, yeah, they're this region of the Tor delta plane here. Right? So this is this parabola here is given by the equation Tor squared equals 4 delta. Delta is Tor squared over 4. Okay, that's what controls the square root here. Right? So yeah, so if we're kind of below the line here, so delta is less than Tor squared. Delta is less than Tor squared over 4. And that means that your Tor squared minus 4 delta is still going to be positive. You're still going to get real roots here. These lambda 1 and lambda 2 are both going to be real roots. But in this case, because lambda 1 times lambda 2 is equal to delta, and delta is positive here. So because remember this horizontal line, that's where delta is 0. We're above the horizontal line where delta is 0, so delta is positive. And remember, delta is equal to lambda 1 times lambda 2. So if that's positive, that means that lambda 1 and lambda 2 both have the same sign, either both positive or both negative. And in this case here, we're over to the left-hand side, where the trace is negative. Remember, trace is lambda 1 plus lambda 2. So if lambda 1 and lambda 2 have the same sign, then Tor will have the same sign as well. And in this case here, we're over to the left, in the region where Tor is negative, so that means lambda 1 and lambda 2 both negative. Okay, so over here we've got this is what's called a stable node, where lambda 1 and lambda 2 are both negative real numbers. And we look at how it works here. So that means that wherever we start, we're always just going to flow down in towards the origin. The blue line is the line of kind of fastest flow towards the origin, and the pink line is the line of slowest flow towards the origin. But doesn't that's just kind of a little quantitative. Wherever we start, we're always just going to flow down in towards the origin. So kind of something that's similar but just a little bit different is what happens if we go above here, above this parabola. This region here is we have a stable focus. Okay, so we're above the parabola, and remember the parabola is where delta is equal to Tor squared over 4, or Tor squared minus 4 delta is equal to 0. And if we're above here, then Tor squared minus 4 delta is going to be negative. Tor squared minus 4 delta is going to be negative, or delta minus Tor squared over 4 is going to be positive. So we get so the roots here are going to be Tor over 2 plus or minus this I omega, where omega is omega is going to be a real number, square root of delta minus Tor squared over 4. But then you're really interested in Tor squared minus 4 delta, so that's going to give you an I omega here. Okay, so there are two eigenvalues going to be lambda plus I omega and lambda minus I omega, and lambda and omega are these two real numbers. Okay. And so then if we write down the solutions, then you're going to get you get e to the lambda t plus I omega t, so that's like e to the lambda t cos omega t plus I sine omega t, using the usual sort of Euler relation between complex exponentials and trigonometric functions. Okay. Yeah, so if we did the kind of intermediate steps, we might have some complex numbers coming out in the intermediate steps, but at the end of the day, x is supposed to be a real solution, and we end up just with a solution written in terms of e to the lambda t cos omega t, e to the lambda t sine omega t. And so we're going to get some kind of oscillatory behavior because of the cosine and sine terms. But here, again, we're still in this region here where the trace is negative, and remember lambda is just Tor over 2, so Tor being negative is the same as lambda being negative, and so this exponential part has a negative coefficient, which means that it's going to die away to 0 as t goes to infinity. So we see that the thing's going to go down, it's going to again go run into the origin like it did in the stable node case, but this time we're going to have some spiraling as well. So here's a picture. Wherever we start, we still flow back into the origin as we did before in the node case, but now we've got a stable focus. We're spiraling around the origin as we flow in towards it. And in this case, this picture here, you can see we're spiraling in clockwise. It's also possible, different kind of solution, you might spiral in anti-clockwise. That depends on the signs, relative signs of the entries in the matrix. Not going to explain the rule for that here. Okay, so that was the stable focus case. We can also have an unstable focus, which is kind of the same in the sense that you're still above the parabola, so delta is bigger than tau squared over 4, and you're still going to get complex roots. But in this case, your tau is positive, and that means your lambda, you still get your lambda is tau over 2, so lambda is going to be positive as well. It means that your e to the lambda t case here, you're going to is going to e to the lambda t, that's going to be kind of a positive coefficient of t, so that will explode out to infinity as t increases. So that means that your solutions are going to now going to run away from the origin instead of running towards it. So here's an example. In this case, all our solutions are spiraling out away from the origin out to infinity, and as they get further and further away from the origin, they're going to get faster and faster. That one was a clockwise one, but you could have an anti-clockwise one instead. So that was the unstable focus, and then the last kind of standard possibility, you could have an unstable node. So this is where we have two strictly positive real eigenvalues, and again, here you get two different exponentials, but both with positive coefficients. So again, the solutions are just exploding away from the origin. So those are the main possibilities. There are also some, that's what we get in each of these kind of 5 regions here that are cut out by this horizontal axis, the vertical axis, and this parabola. But you could be on one of these lines. I mean, one particular possibility is you could be on this central axis here, where tau is equal to 0. And that's kind of an interesting case. That's what's called your solution is called a center. So that's where the solutions actually solution curves are closed curves. They're ellipses, and so if you run around one of these solutions, then after a little while you get back to where you started, and then you just keep going. So you don't spiral in. If you were in the right half plane, if tau was positive, then you would be the solutions would explode out to infinity. If you're in the left half plane, where tau was negative, then all the solutions would run in towards the origin. But here we are kind of finely balanced with tau being equal to 0. In that case, we don't go in towards the origin or away from the origin. We just rotate around it like so. Other possibilities, we could have a semi-stable node. Semi-stable nodes like this, where instead of flowing in towards the origin as we do in the stable case, we don't flow in towards the origin. We flow in towards this particular line here. That's that's the thing that can happen when delta is 0. So delta is 0 means that one of remember, delta is equal to lambda 1 times lambda 2, the product of the two eigenvalues. So this is the case where you get where one of the eigenvalues is 0. And when one of the eigenvalues is 0, you have a conserved quantity. You always run along these red lines. You never escape from the red line that you started. final possibility. You can have this so-called improper, improper stable nodes. That's kind of in between a focus and a in between a node and a focus. And the deal in this case is you flow in towards the origin, but you just flow along straight lines. There's none of this curving. So that's the last of the possibilities. But the general picture is, you've got all the different possibilities, the general different qualitative behavior of these linear systems. It's all controlled by by these numbers, Tor and delta. Tor is the trace of the matrix. Delta is the determinant of the matrix that appears in the differential equation, and sort of general features of the solutions given by where the Tor and delta lie on this little diagram here.